With that, I would like to make a short introduction to our first speaker, which is Professor Emeritus Yoav Benjamini. This is very exciting to have you with us. I'm very glad to welcome you from Tel Aviv University to our autumn conference. Your work with selective and simultaneous inference with multiple comparison, and your work on developing useful tools that can aid researchers tailored for the special needs in medicine, epidemiology, genomics, bioinformatics, neuroscience, and behaviors is extraordinary. We acknowledge the ongoing war between the State of Israel and its neighbors and the Palestinian territories, and the very real and widespread human suffering involved. But the Swedish Statistical Society is a not-for-profit organization, and we're dedicated to the continued development of practice of statistics. Therefore, we welcome you, Dr. Benjamini, as a statistical colleague, a practitioner, and a researcher in statistics, and I'm very much looking forward to your presentation. And with that, I will leave over the word to Matthias.
Excellent. Thank you so much, Nancy. And as Nancy already mentioned, a very warm welcome, Dr. Benjamini. Dr. Yoav Benjamini is, as Nancy mentioned, a professor emeritus of applied statistics at Tel Aviv University. He is best known for his development, together with Josef Hochberg, of the false discovery rate, the FDR criterion, and for which he also received the Rousseau Prize in Statistics, a very prestigious prize being awarded in Belgium every other year. He is a member of the Israeli National Academy of Science and an international member of the US National Academy of Sciences. And with that, I welcome Dr. Yoav Benjamini. Welcome.
Thank you. Thank you for the invitation and the opportunity. We know that this practice of Zoom conferences is what we have learned to organize during the COVID years. It's also a way for us to continue to participate constantly in whatever international activities are going on. So thanks for that. Okay, so the title of my talk, I was asked to talk about the future of statistical inference. And I decided to talk about the future of statistical inference that lies in applied statistics. And this is the main theme of my talk. I'll argue that the challenges, the statistical inference that arose from addressing applied statistical challenges are important, and they should guide us into the future. So I'll present first some historical perspective, very few, and I'm sure you know all about them. I'll talk then about my experience with selective inference and give 5 examples, some longer, some shorter. And as I said, since I believe this will continue in the future, I'll talk about a few practical implications from this point of view regarding the way that we should progress in statistics. Well, we all know and teach about Gossett, his work experience in the brewery, and how this has generated the students' T distribution. We know that Fisher worked in agriculture, and this directly affected his important publication, Statistical Methods for Research Workers. And his deep involvement in genetics is reflected in the Design of Experiments book and related work, including his suggestion of fiducial inference and so on. Fisher also had this continuation of work about students' T, and he gave a full mathematical proof of the distribution of the T statistics. And this has led him to the publication of Mathematical Foundation of Theoretical Statistics back in 1922, which had a huge influence on our profession, I think, because it coronated mathematical statistics as the loftiest way of doing statistics. And this is not in the tradition of Fisher himself. Box and Jenkins, in their time series analysis, focusing and control, wrote in their preface, over the last 10 years, the authors have worked with real data arising in economics and industry, and by trial and error, and by sequence of interaction between theory and practice, have attempted to select, adopt, and develop practical techniques to such needs. So we see the strong connection between the involvement in a specific domain of practical work in statistics and the theory that was developed in view of that. It's obvious to mention Koch's involvement in medical research that yielded proportional hazard models, among other important theoretical contributions. And I'll mention Donohoe and Johnston's work, who at least I heard Donohoe say that their work on denoising signals by wavelets and soft thresholding and so on started from interaction with chemical professions and chemical analysis. So that, as much as historical mentions goes, and I will talk now about my experience with selective inference. And first, the way I got into selective inference is not by being Tukey's students, although I was at Stanford and he was my mentor, but actually Yossi Hochberg, who was an expert in the theory of multiple comparison procedures and wrote a fundamental theoretical book with Tamhane in '87. But later, he was also the head of the statistical laboratory at Tel Aviv University, where he was responsible for the analysis of a large clinical trial, where 2 blood pressure medications were compared by many, some more than 100 quality of life outcomes. And being an expert in multiple comparison, he tried controlling for multiplicity using the best methods that he knew, including his own, the Hochberg method, and they all yielded nothing. The point was that the 0.05 used in clinical trials divided by more than 100 was much too low for showing any result in this area. So working with more generally about multiple outcomes, or sometimes they are called endpoints, realizing that if only part of the null hypotheses are true, m not less than m, and the fact that it is enough then to use 0.05 divided by m not, both for the Bonferroni, for Hochberg's procedures, for Hond procedure, and so on and so forth. Actually, the number of true null hypotheses can be used, but do we know it? Well, when m is large, m naught can be estimated from the data. And that is an important point and benefit from having a large m. And this was utilized by Sweater and Schotfeld and by our own work before the false discovery rate. But that made us actually get triggered by Zoric's paper, which yielded our first version of the false discovery rate, where R is the number of rejected hypotheses, number of discoveries, and V of these are in error, are false discoveries, and our first definition was the expectation of V divided by the expectation of R. That was very nice, and we sent the first version, I sent it to Tukey this way, but then I realized that if the treatments do not differ, if all null hypotheses are true, then V equal R, so this definition of FDR is identically 0. And so no procedure can always control the FDR at the desired level, and so it will not be useful for medical research. So when going back to the medical problem, our next round brought the familiar definition of the false discovery rate as the Q being the proportion if R is rejected, and getting the value of 0 if R is 0. If nothing is rejected, Q is the false discovery proportion. I will use this term later in my talk. And the average number of type 1 errors over the rejected ones, FDR, is the expectation of Q. Now, the pH procedure that controls the FDR also controls the probability of making even one error when the treatments do not differ. This raised a lot of theoretical challenges. First and foremost, more adaptive methods for estimating M0 were offered. There actually were with some review, almost 20 different methods, but proving their properties, the point not of M0 as an estimator, but when replacing M, was and is a challenge. There are two proven FDR control under independence, work by Story, Zugman, and Taylor, and our work with Krieger and Nicutielli, where something is proven. But for the many more proposed, and some of them might be even more powerful, there is no only partial proof, especially under independence. There is still a growing theoretical literature, for instance, sequential work and so on, but it is still open. The second issue is that outcomes in clinical research tend to be positively correlated rather than independent, and the pH was proved for independence in 1995. Hence the importance of offering FDR control in this setting. Positive regression dependence on a subset of null, PRDS, is a criterion we offered with Dani Nicutielli in this paper, and this holds for normally distributed, positively correlated, one-sided test statistics. Here, the pH procedure satisfies that FDR is less or equal than the desired level. But for instance, Stuckey, when he confronted a pairwise comparison in a problem in educational research with more than 500 pairwise comparison, even though he argued earlier that always one should control the family-wise error rate, really got a bit despaired here and moved to control at 0.5, half, not 0.05, 0.5 level. But then he realized that the FDR, the pH procedure, might help, and he suggested to use this method, supporting it by simulation. Two-sided with any correlation, that is the absolute value, when some mu's are positive, are different from 0, some hypotheses are true and some are false. There is a lot of evidence and support for that, but for both problems, the theoretical problem is still open. Dependency may not only be proven for the regular pH procedure, but dependency might be utilized, for example, by resampling. And there is a lot of work on that, including a whole book by Dudois van der Laan about using this kind of methods and proving their properties to address dependency. And more recently, the work of Candes, Emmanuel Candes, and Feugel-Barber on the knockoffs, and the many following work is a way to trying to address dependency, which is general dependency one might be utilized in genomic research. My second example is microarrays or gene expression data. I was first confronted with the idea when someone came to our statistical laboratory, some researchers, and showed us the plastic sheet on which there are 26 spots, one observation per gene, per pair of treatment versus control. And they were just put on a slide and analyzed. And this was my first encounter with that. We started to analyze it after the head of the was despaired with because there was one observation in each group to compare per gene. But that led us to realizing that there is some important problem that need to be answered. We started to work on it, but in the meantime, the technology grew faster than the statistical analysis. And this is the reported paper per year from genetics, the number of gene expressions reported in that paper. This is one per year. So initially it was 1096 sheet and so on. It grew, not the logarithmic scale here. Microarrays were invented in 1993, and that brought us here. But statistical analysis trying to address the multiplicity problem for the first time was in 2001, where the number already got to 6,000 or 8,000 genes per analysis. There were various groups of statisticians that got involved in the actual analysis of the genomic data in Stanford, at Berkeley, Melbourne, and at Tel Aviv. And of course, working with the FDR and version of FDR was one important way to deal with the problem. But it also, the problem set up the mixture model for microarray and beyond, because it's used not only in microarrays. In the frequentist approach, we have H1 up to Hn, our M hypothesis about differential expression out of, sorry for the double F in the off, out of M gene tested by P1 to PM. M not of them are unaffected, so HI is true. When HI is true, PI is uniformly distributed. The other are differentially expressed, with PI having distribution G1, which is stochastic smaller than U. In the Bayesian approach, corresponding to M naught over M is P naught, which is the probability that gene I is unaffected, that is that HI equals 0. If we further assume that HIID, we have a Bayesian primer, which is the probability that HI equals 0, with the above P naught. And the distribution of each PI is therefore a mixture. P naught is mixture of P naught times the uniform plus 1 minus P naught times the other one. Or if we look at the observation themselves, that is, take them back to the Gaussian distribution or look at the real distribution, then we have the distribution is P naught is times F naught plus 1 minus P naught F1, or the density Fz, which has this form. This is the mixture model. And this is widely used by most of the people working in the area and away from it. Bayesian interpretation, for example, for FDR, for the rule reject if PI is less or equal to some constant, then the positive FDR is the probability that HI equals 0, given that 1 was rejected, given that PI is less than or equal to alpha. And this was used by Story to show it. Essentially, when M goes to infinity, with M naught over M going to P naught, which is strictly less than 1, then these notions of positive FDR and regular FDR coincide. But there's a lot of theoretical work around this interpretation and this work. F1 emphasized the local version, called it FDR, when we're talking about the probability, or talking about little FDR when you talk about the ratio of the densities, which they call the local false discovery rate. And this is the posterior probability that the gene with score Z is unaffected. In the Bayes approach, you specify F1, P1, and then F. In the empirical Bayes approach, you estimate P naught, just like estimating M naught. You estimate, therefore, you get an estimate of F if you assume F naught, or in later work, F1 even suggested estimating F naught, at least up to a tilde. This is the content of the whole book by Efron on analyzing complex data questions. So you see that the work with genomic gene expression related work has had a lot of influence on theoretical and inferential problems. Going to my third example, it's related to my involvement in exploratory behavior of mice. Open field behavioral tests are extremely important. It's a tool in research in neurology, in drug development, physiology, and so on and so forth, where you use the mouse as a model and test it in order to understand both the scientific problems, but also pharmacological properties and so on. Here you see an example of a setting, which is the open field. This is a setting we built after experiencing with the more box type tests that are being used in the industry. The mouse is there. You can see it up in the top. There is an opening. He lives in a box where he has everything he needs. Still, when the door opens, he will go out exploring the new environment. And as you can see, he will explore it first to the left, picking out of it, going out, making stops, progressing, but then at some point, returning back home. In fact, my involvement with Professor Ilan Golani started when he came to our statistical laboratory and said that his rats know how to count up to 8, and he wants us to prove it by statistical methods. So that got me involved, and our involvement went on for about until he passed away recently. One can measure all the properties like the number of stops, the length of the length of the pass, the proportion of time staying near the edge of the arena, and so on and so forth. And at some point of time, we were interested in the replicability of such summaries and did it comparing between 8 inbred strains of mice at 3 laboratories. 1 ours at Golani et al., and 2 at the United States at Maryland Psychological Research Center at NIDA. The result of the comparison used me to demonstrate the importance of controlling for multiplicity, but here I want to show another aspect stemming from this experiment. Greg Elmer, one of the participants, followed with gene expression measurements in regions of the 5 regions in the brain of each of his mice. That's what he had. And his question was, what genes and in what brain regions are expression levels correlated with a specific behavioral taste? We had 17 behavioral tests. There were 5 regions and 27,000 genes. Altogether, a question about 2.2 million hypotheses. And that was the first time that actually we got the idea working with them. And Danny Gutierrez was in that, Anat Reiner, another student of mine was in that. And the first time we talked about hierarchical testing. That is, we can use the fact that we know that there are differences in the different measures and different endpoints between the the strains. So maybe first we shall take the genes by brain region hypothesis, about one-way hypothesis here, test them, and only follow up those gene by regions that we found something in them. And then we will test the correlation per each rejection pair. Okay, the correlations were not used here, only the expression level in the first level. Now, this led to this display of the results. There were 137, if I'm not mistaken, just pairs. Here you see the genes, genes by brain regions, and then the different, the 17 measurements of the behavior, like distance traveled, or the turning, or the proportion at the left, and sorry, too fast. And what you see here is the significance based on the false discovery rate, or the Q values adjusted for that, and you can see the positive one, the negative one, according to the different levels. But we had to support this by theory, and here I want to point the extremely nice work that we did, that Daniel Yekutieli did in terms of theoretical work. We did put the general hierarchical structures as that of, you have one family, and then there are children hypotheses in the family. Some are selected, being significant, for example, and you follow only those that are being selected. And there is a root to the tree, but the tree can progress with L at more and more levels. Now, what are the meaningful discoveries? Well, there are, if we do the testing, starting from the top and going down, we have 3-level discoveries. You see there are 4 of them. That is, we count discoveries at each level. We have L-level discoveries. You see all discoveries in the same level, meaningful discoveries. And we have end nodes discoveries. This is the last one in the path, and this is the last one in the path, and this may be a refinement of this one. So there's no interest now in this. Rather than that, we have interest in the last one. Now you see the number of discoveries changes, and so counting errors out of the discoveries also changes. And here comes the beautiful theory that Dani Yekutieli has presented. For a 3-level FDR, if we do FDR BH testing at Q prime, the real Q is twice times 1.44 times this Q. And that is no matter how many levels in the tree, assuming independence of the test at all nodes. One can think about the progress of science going in this way. You see the inflation is extremely short. Not most hypotheses in science are false, as was argued by Ioannidis. For level N FDR, no Q-prime, no use of Q-prime in the BH procedure can guarantee anything, but the false discovery portion can be estimated. For endpoints FDR, Q is 1.44 times L times Q, and L is the number of levels in the tree. So here we see that increasing the levels in the C for endpoints is something penalty. But going back to our behavioral genetics data, we could use 0.025. The 1.44 is a theoretical bound, and it was shown by simulation to be very close to 1. And that is what we use to show the previous display. Okay, I'll continue with family of families. The theory continued with 2-level trees. But again, it was motivated by the fact that the structure that we've shown that there are independent tests is not there at each point of the tree is not very common in practice. In more practical situation, only the endpoints at the bottom of the tree have p-values, and they are combined to families of families up a tree. And we were talking about two levels of a tree, about a particular problem that I'll discuss shortly. So Pij are available for the end hypothesis at the lowest level, and the I here indicates the family. So Pij for all j is one family of hypothesis. SP is the selection of procedure of families based on this pair value, and the random number of families selected is denoted by this. And now the goal is to control the false discovery proportion on the average over the selected families. So for each family, we have the false discovery proportion, its false discovery proportions, and we average them over the number selected. And we wish this one to be less or equal to Q. So the tests at the lowest level are used all the way up the tree, using combination tests in upper levels. Is there something in that family before we ask whether there is something particular in the family? The method developed was to test the family using BHQ at the family's level, select the rejected ones, and then within each selected family, use the BH at the lower level, Q times R over M. So here you see the adaptiveness. If you select all of families, you need no correction inside the family. But if there is only one family selected, then R is 1, and you actually have Bonferroni-like approach going down the FDR levels. An important application for that, and which we used also as the motivation, is the level at what is called EQTL, where the level of expression of each gene may be modified by the structure of the SNPs identified by its location. There's also another version looking at distal ones, but let me concentrate on this one. So the question is, what gene's expression is affected by SNPs located nearby? Okay. So here are the gene expression, and we would like to know for what genes we have this phenomena. Then, at the second level, we want to know by which SNPs are they affected. So for each such one, we have local SNPs, and we ask for which one they are. So we test this level. These are two significant ones. We enter only these ones, and there we try to identify which SNPs affect these genes. And this was the 3PH methods suggested working with Sabati and Peterson and Marina Bogomolov. But there is an even greater challenge from EQTL. And this is the same problem, but not in one tissue, but in more than one tissue. Actually, 3, 4, or even 5 tissues, but that means requiring 3 levels. And that question have brought us to discuss the most general theoretical question, testing hierarchical trees with various number of levels. But, and so we had some work with testing family of families, extending it to general 3BH, more than 3 levels. But the problem became very important, and so a lot of other researchers started to work on this question. And there are suggestions like the P filter, where using prior knowledge, both the structure and the importance, by Ramdas, again, Foigel-Barber, Weinreich, and Jordan. There is the STAR method, hierarchical inference via conditioning of Heller, Krieger, and researchers at the research center, the Cancer Research Center in Washington. And actually, our interest in conditioning started from Heller's involvement in fMRI research, but I wouldn't go into that. And addressing endnotes on hierarchical tree, again, by Katsevich, Bogomolov, and Sabati. And it's still going on. So there are, this is still an active research work of people working on the theoretical challenges arising from testing, hierarchical testing of trees. My last example will be on medical research again, and it's related to the new guidelines for statistical reporting in the New England Journal of Medicine. The new guidelines discuss many aspects of reporting of studies of journal, include a requirement to replace p-value with estimates of effects or associations, a 95 confidence interval when neither the protocol nor the statistical analysis plan has specified methods to adjust for multiplicity. And they give an exemplary study from Manson et al. That also appeared in the New England Journal of Medicine. The study was about fish oil supplementation. There was no significant effect in the primary endpoints, but as far as the secondary endpoints, there were 4 out of the 17 that the confidence interval didn't cover 1, which means no effect. These 4 were the ones cited by another paper that cited only these 4 out of the 17 secondary outcomes. And this points at the problem that selective inference by confidence interval is totally ignored, even though it's not only that the confidence interval reflect, in this case, p-values or hypothesis testing, but the fact that they lose their coverage when restricting them only to their selected. So to address the selection bias with minimal power loss, we suggested to use the false coverage statement rate that controls the expected proportion of the non-covering intervals out of the convergence selected. And if R are selected using the pH test, then we use 1 minus alpha modified by R over M and create the plus minus appropriate intervals. And then there are intervals cover 0 if and only if selected. But in the original paper, we say Yekutieli, we noted that the selection can be much more general. In particular, in New England Journal of Medicine, the R selected outcomes for emphasis are the marginally significant at alpha 0.05. So use this R and create symmetric intervals. And that was my suggestion to New England Journal of Medicine statistical editors, which wasn't accepted. But confronting the Israel cloud seeding experiment, which I was involved in this kind of research, meteorology, ever since I was in graduate school. But after 30 years of operational seeding, a carefully designed new experiment was conducted in Israel and held for 7 years. David Stamberg and I were the methodologists, were the statisticians, and there was a 1.8% increase instead of the 12% increase. The p-value was 0.4, and the confidence interval was minus 11 to 16. Our conclusion was that there is no point in continuing. But presenting the result to the board of the water authority, some responded, but the confidence interval includes 16%. It's even bigger than the 12%. I mean, why shouldn't we continue with operational seeding of clouds? Well, we had a long time explaining this, and ignoring such objection, operation seeding in Israel was stopped. But this brought me to think that the adjustment of symmetric confidence interval, adjustment for selection, increased the potential, the seeming potential. They extend too wide in their direction away from zero, giving a false impression of potential large benefit. So for FCR control, we found that one can merely use 1 minus alpha r over 2m level interval towards zero, but a regular interval away from zero, like irregular intervals. And these CIs address post-control, and is the work of Frosting and mine, but it is based on many other theoretical works, and is continued by work relying on conditioning that do not address the two sides of the problem in the same way. And what it did in this example that I showed before is that after the adjustment, these remained at the same point, and only one of them got confidence interval got very close to zero. So I will just summarize that FDR methodologies and theory were developed in response to scientific challenges, and then industrialization of the scientific process made these challenges more complex. And this, in turn, raised more theoretical challenges. So more generally, I would like to comment, and in the first few slides, wrap up my talk. New data analysis challenges arise constantly nowadays. New recording devices appear, new smartphones, microarrays technology. The scale of the data collected increases, time series, videos, integrating different sources of data for generating answers, MRI and ultrasound, EMR and daily health data, fMRI and electrodes on the scalp, and so on and so forth. And all of these create challenges that result in theoretical inferential challenges. Assessing and communicating relevant uncertainties involving the answers we gave to a problem. Experimental design for accelerating large language models may be another example, but it requires involvement of statisticians in actually doing and using LLMs. The point is that theoretical inference challenges will then arise naturally. But getting to understand the needs of scientists in different scientific disciplines or in managers or engineers is crucial. And better do it while wetting your own hands in the data. What is it the current attitude? I'm afraid that young statisticians seeking research careers are discouraged from getting engaged in applied work. I have my own experience, Dr. Frosting's thesis. It was jointly supervised, and part of his research was building a model for length stay of preborn babies using the entire data available in the intensive care world. Excellent work, already published. My co-supervisors, who also thought that the work was great, was against including this work in the thesis, saying it will not be received well in his job talk. And unfortunately, this reflects the current attitude. I was asked to comment, to present a talk at the 100th session of the International Seminar on Selective Inference, being held almost weekly since the corona epidemic. I reviewed the 99 papers, most of them by young PhDs, and you can see it's from diverse departments, including Berkeley, Stanford, Penn, CMU, both the best department and Florida, MIT, and so on, and Yale, which is lower department. But the point is that all across the board, The work involved testing, confidence interval, estimation, every part of the inference. Looking at the areas of application, there were 44 seminars that included application in genomics, medical health, and so on, and one in biology, cosmology, only one in COVID-19, amazingly, but 55 had no application mentioned in the talk. So what I would like to summarize is that working on applied problems involving the analysis of data should be encouraged. Papers appearing in non-statistical journals should receive appropriate credit. When I came to the Department of Statistics, they say that they do not count. Then they said, okay, they will be counted at some alpha, but maybe a third. Along my stay at the department, I managed to increase alpha to get close to 1. I'm not sure it will stay close to 1. But don't separate the list of published papers to applied and theoretical ones, but because it already gives inferior meaning to your applied work. Now, all applied work is not of equal importance or equal quality. Assess the quality of applied papers and the contribution of the statisticians. But recall that statistician will rarely be the first or the last author, so you need to read the paper for that. Adopt reviewed conference as a mode of publication. That might help speed up the work and not discourage young people to work in that. And finally, encourage the hiring of statisticians who can and want to work with data. I will leave this one maybe to questions and simply thank you for your attention.
Excellent. Thank you very much, Dr. Benjamini. It was very insightful to hear a bit more about how to actually go about understanding the problems arising with statistical inferences. We are now opening up for questions. So if you have any questions, you can either type them in the chat box or you can simply unmute yourself and ask the question of Dr. Benjamini. I will start off with one question. Towards the end, you said you presented the result to government, I assume, regarding the seeding of clouds. And isn't that more a question of statistical literacy among the recipients and how to explain statistics and data rather than it being a fault with the data itself or the results?
I think, well, first of all, there is this point of literacy, no question. But this point is there for physicians as well. And for readers of literature who read only the abstracts and see the highlighted confidence interval. But beyond that, there is a theoretical fundamental issue. When we look at confidence interval, there are 3 goals that actually Tukey discussed about them. How do we use confidence interval? And they say the first, and they are ranked by importance. The first is to say, can we separate away from 0 in that direction? If we cannot separate, we should have a confidence interval as short as possible. If we can separate, and we try to separate it away from 0, the third goal is to keep the other side, the outside one, as inside as possible in order not to give this expression. Now, this calls for non-symmetric confidence interval. When the goal is to show that something is positive. It's not true if we are indifferent about the direction, like in gene expression. Then there is no difference. But when we talk about medical research, or when we talk about this experiment where we want to show, the interest of all the crowd was that the reason effect, for 38 years we've been doing that and investing money in that. Then one maybe should think about non-symmetric confidence interval that give more importance for that. And this is, in fact, we have some work ongoing, especially Ruth Heller is working on that, and regarding the medical research with some other researchers. So I think there's, beyond the non-literacy, there is also an inherent substantial problem.
Okay, thank you so much. We do have a question from Nancy Steinbach.
Oh, sorry. Technology. Thank you very much for a fascinating presentation. I'm not familiar at all with genomics or areas within, but I was struck by, I mean, the amount of data that you had to work with, and the innovation you had to create in order to manage all these millions of hypotheses that you had to test. Have you thought of trying to recreate some of that work using other technology available today, and see, could you have done a similar innovation today based on the technology you have, or would you have carried on, with the fundamental knowledge you had, then you being quicker now, if you understand what I'm trying to say? That's one question. And the second question I had is also related to applied statistics. I only have a master's degree in statistics, but I was never comfortable with the theories. I needed the actual data to look at to get a feel for what I was doing and understand what was going on. Yes, for me it worked out okay. But I see so many analysts today that don't actually look at the data. They can do fantastic models and do fantastic analysis. And then I ask, have you looked at the data? And they don't understand my question. So I don't know if you've seen some of those aspects too, where they're not only discouraged perhaps to actually apply methods and theories, but also they don't learn how to apply it and see if there's anomalies in the data sets and so on. If any of your experience, if you have found similar issues. Thank you.
Okay, so one story and one slide. And I wonder, and before that, I wonder if you had some particular technology in mind, but we use the same ideas. I didn't have time to present it in fMRI, functional MRI, where you analyze the brain. And when you're talking about connectomes, that is not only whether there is activity in a particular voxel, but if there is an activity or in the connection between two. So you're talking there about even larger problems. And so bringing regions into play, so regions of and the interconnection between them. And they're all very much prone for using this type of technology. But each time there is a new technology, there is a new practical challenge, and there is a new theoretical challenge. You can build upon them, but that's why I think that statistics and inference will remain a lively one in the future, especially because every new area starts with a small data set, usually, like the 96 points on a slide that I discussed. And then it starts to grow up and to grow up. And our power is to look at the data, and it's easier when it is small, or use sampling to get a small, but look at the data. So if you allow me to share again, and I will go to the slide that I didn't show, just to give you an answer. So when I look at data science, and the first discipline in data science was statistics, and data was a major part of that, looking at the data, actually getting the data, generating the data, the design of experiments, sampling, and so on. And then there was computing, summarized relationship, assessing uncertainty, visualization, decision-making, prediction, and I've left probably a few things aside. And as I said, Fisher inference was to talk about theory of inference, which is identified by let X be a matrix, or let Xi be a series of independent test statistics having a distribution F. Somehow, the theory of inference became mostly identified with statistics, while most statisticians, certainly applied statisticians, worked in this area. And actually, it was the major contribution of Tukey, who presented exploratory data analysis as something of importance. He was talking about a batch of data. Doesn't matter whether it is a sample, whether it was derived by design, simply a collection of data. And then you don't have assessing of uncertainty, you don't have decision making, you don't have prediction, but you want to understand what is going on in the data. And I think exactly the same meaning is data mining, which grew from that. The only difference is the data mining, there was large available data, usually accumulated for other reasons rather than for looking for insight into data. But other than that, exactly the same things were done. And then came big data. Big data is just data mining with larger available data. It is true. Scrapping, you had to learn about scrapping and other methods. Working with huge computing became complicated, but it's essentially the same thing. It is not surprising that when data mining, the term data mining was popular, the prediction was that statisticians will be the most desirable profession. And that was indeed the case, because there's no difference between this and this. And then there was big data, and somehow we disappeared from this area, unfortunately. Machine learning, which grew later, well, that became scrapping. But data, and that's what the anecdote I wanted to say. I chaired a committee on strategy for data science, research in data science in Israeli universities. And that there was a collection of statisticians, people working in machine learning, people working in big data, and so on and so forth. And one of the machine learning professors came with me to the Israeli Bureau of Statistics to discuss how can we use their data and make it available to university. And at the ending of the meeting, he said, wow, I didn't realize that so much effort goes into getting the data, cleaning the data, arranging the data, so we will, at the end, we will get X to continue with. So even machine learning is scraping the data, but data is not as important, and computing, decision-making, and prediction is. So that's my view. Mm-hmm. As long as we keep on working or having a good hand in data and the scientific problems and so on, we will not remain a branch of mathematics and end up with two statisticians in the Department of Statistics, as happened in the 60s and 70s. So that's my other prediction for the future. As long as we don't, then we have a good future.
Excellent.
We'll stop sharing.
We thank you very, very much, Dr. Benjamini, for joining us and sharing your experiences with some of the upcoming problems and possibilities as well for statisticians. I think it ended on a beautiful note that we are still relevant and needed even when talking about machine learning and AI.
Yeah. Actually, thank you for your statement, not your statement, prior to my talk, that I hope that you will continue with this approach of shielding science from politics in the future. I do want to let you know that in any case, the academic community in Israel is a stronghold of democratic and liberal ideas in Israel. But that's irrelevant in some sense and very relevant in another sense.
Indeed.
Thank you.
Thank you very much. We truly appreciate having you with us. I see that.